Today I'm going to be showing you how to measure, one of the way, how to measure a crystal. Okay, first of all, what is crystal? Crystal is a natural material which gets ground into a specific thickness, and because of its nature, when you apply the voltage of specific frequency and amplitude, the crystal will move in the rhythm with the frequency and the amplitude, or vice versa. It will, when you apply the pressure to it or the movement, it will generate the voltage. And of course, any crystal has got two resonant frequencies. One is for a series, because it consists out of series and parallel resonant circuit inside. So it's got two resonant frequencies for a parallel and for a series circuit. Now, that particular phenomenon, what they do is, the clever people, they use it and they call it the overtone. So most of the manufacturers, if you look at it over there, crystals usually, they depends how they manufacture it and what application. Say from 1,8 to 40 megahertz, you get the fundamental frequency. It can be manufactured. Then you get from 20 megahertz to 105 megahertz, which is very, very rare and very difficult to manufacture. The reason why, because of such a high frequency, and the crystal becomes too thin and too brittle, and then it can break because of such a high frequency vibration. So they use third overtone or third harmonic, should I say. So one is going to be, but I'll come back to it just now. Like, for example, the ceramic resonator crystal shows 50 megahertz, but it's meant only to be operated on the third overtone, not as a fundamental frequency, which fundamental frequency is about 9 megahertz something. But nonetheless, I will show it to you just now. Now, you get different shapes and sizes. You get the HC49U, then you get the miniature one, HC49CS, 49S, should I say. Then you get, of course, very old package, which is not really manufactured any longer, but I'm privileged to have some in stock. Then, of course, you do get the, ceramic resonator crystals. You get them with 3 legs, you get them with 2 legs, different colors and so on. Now, what's the primary difference between the metal and the ceramic? Oh, well, this is more accurate, okay? Gives you like a, if you look at it in the specs, temperature tolerances and things like that, it can be like a 50 parts per million, and depends, where you actually apply it. Obviously the metal one will give you, because it's shielded also and things like that, from external protected from the environment, electromagnetic waves, etc. and so on. Where this one here, it is made out of ceramic, substrate, on a ceramic substrate. So it does operate, it's quite accurate, but not as accurate as these particular crystals. Now, even these crystals, you do get them in surface mount. Now, let me just, flip it over so you can see the bottom. You can see it. And you'll see how you actually measure it, because I have made a special jig for it also. All right, now let's see, how do you actually measure them? One of the ways to measure the crystals would be using an old-fashioned way, and it's been used for decades, and it's still used today, basically with a dip meter. And of course, where the crystal is resonant, I will get the dip of the needle, and that would be my frequency. And then I would use frequency counter, attach over there, and then actually measure and see precisely what is the frequency of the crystal. Of course, this is an old way, and not many people even know the dip meters, but not, or have them, but nonetheless, it's still widely in use. Among radio amateurs and electronic enthusiasts and so on. Okay, second way is of course more sophisticated way, that is using the basically scope, function generators with the RF generators, type of thing, which is an expensive way of doing it and is beyond many people. Nonetheless, so I come up, well, I didn't come up, I just made, and I've been using it for quite some time, I made my own, a much cheaper sort of way of measuring and quicker to set up and whatever. Small, little, and I decided to start making it and selling to the customers because everybody is asking for them, and they're not easily obtainable. And yet, and it's quite an accurate actually little bugger. Now, basically what it is, you got the power source, you got the clever electronics, and then of course you require a frequency counter. Now, the more zeros you got on the frequency counter below a point, the more accurate measurement you will obtain. And of course, there will be some discrepancy, but only in about hertz or tens of hertz and things like that, due to the sort of stray capacitance and inductance of the actual test jig. So there will be some, but that's insignificant for these type of crystals. Type of thing. So now how do you actually, you connect the battery, and then let me just connect the frequency counter. I'm just going to connect the frequency counter. Let me just do it quickly. Okay, so the frequency counter is connected and it's going into my frequency counter over here. I can measure up to 1 gigahertz on this particular, which is fairly accurate. Of course, I got another one, but this one it's here on the bench, so I'm going to use this one here. All right, now let's take one crystal. I'm going to take this particular one and start, say, from 1,8342. So I take the crystal, basically, and then what I do is I just plug it into the socket, okay, and then, sorry, let me just... Okay, and then let's see the reading. 184309. Okay, where this one is 18342. Okay, there is a slight discrepancy. That's in megahertz, and so is this in megahertz. Okay, which is 1,1 megahertz, 84309 kilohertz. Type of thing. So this crystal is 100%, although there is a slight, on the last digits, a slight variation that's insignificant, as I said, due to the, stray inductance and capacitance, which detunes the whole, and also the environment, the wiring and things like that, surrounding sort of the instrument. Okay, so I'm going to remove it and put it back. Now let's go to say 11 megahertz. This one that I'm taking, it's 11391. Okay, let's plug it in and see what it says. Okay, now it's in 11,38903. So it is very close to 139, which is perfect, as I said, due to the stray sort of influence of the test jig. The socket and so on, because I made it universal for different spacings and so on. I could have made it a bit smaller and shorter, but this way I rather sacrifice 10 hertz on a 14 million type of 10 hertz than battle with the crystals, to be able to test them quickly and so on. Okay, so now let's take, say, this one here, HC49S, okay, which is a low profile. Now this particular one, it's exactly 24 megahertz. Let's see what happens. Okay, I'm just going to plug it in. Okay, I plug it in and let's see what it says. 239951. Very close to what you call it, 24 megahertz. So this crystal 100%, and so is this jig. Very precise. Okay, let's put the crystal back again. Let's try, say, this is a 4 megahertz, okay. So I'm going to take a crystal that's a ceramic resonator crystal, and I'm just going to plug it in. Okay, so it's plugged in. Let's see. And the one that we're going to measure, it's a 4 megahertz. So let's see what it says here. Okay, 3.88 megahertz. Okay, that's nearly 3.9 megahertz. So we're talking difference of something like 100 kilohertz, just over 100 kilohertz difference, sort of what the resonator is being printed on, designed and made for. But it makes no difference. It's good enough. Does not matter is because this type of ceramic sort of resonator crystals, although it's made for a 4 megahertz operation, yet it measures 3.88275 megahertz. They're slightly under 4 megahertz. It won't impede the operation of the microcontroller because or any sort of timing circuit because only the rising and the falling edges of the signal are actually used for timing. So it's not so critical. And even in a data sheet, if you look at it, you will see that it allows you the variation. And this is very close to 4 megahertz for this type of crystal. Ceramic resonator crystal. So even this one here, it's 100%. That was a 2-pinner. Let me try with the 3-pinner now. Let me take this one here. Okay, this one has got the 3-pinner, and okay, let me just insert it. Okay, there we go. Oops, sorry, what am I doing? Okay, let me just do this. Now, which originally it's been designed for 4 megahertz. You can see actually on the instrument, well, from my sort of measuring instrument, which is fed into the frequency counter, that it shows 3.860 whatever. Now there is a discrepancy, and that is a normal thing for these ceramic resonator crystals, to differentiate by 100 or so, 200 kilohertz and so on. As I've already sort of mentioned but earlier on, due to the requirements where they are used. And in the data sheet, you will again see that that is the allowable sort of variations from what is actually printed on the ceramic resonator crystal. Because you must remember one thing, it's very easy to manufacture, much easier than the actual sort of these metal crystals type of thing. And it's only a fraction of a price of this type of a crystal type of thing. So the cost factor, it's very important, and it does not matter that it's not exactly 4 megahertz. The important thing is it's used, it's fairly stable at that particular frequency, although it does not give exactly 4 megahertz. But nonetheless, that is acceptable in the electronic industry and in any sort of designs where the crystals are required, specifically in the microcontrollers and things like that. All right, so now let's remove this one here. Let me just remove it. Okay, I'll put it over there. Now, what else should I do? Okay, let me show you this, the very old type of a sort of crystal, which is, and the housing, it's not manufactured any longer, as I said, because it's bulky and the technology has gone, you get them in surface mount. Sorry, I dropped it here. Let me just pick it up. Okay. And you get them in surface mount, type of thing, which are, as the things are getting smaller, there is a requirement for smaller sort of packaging and yet same accuracy and things like that. So let's try this one here. And this one, I've got few of them, and I'm actually privileged to have them because they're very, very, very old. Tapotin, the way they were packaged and the way they were made and so on. But let's test it. This is about 4,433 megahertz. Let's see, what does it say? Okay, I'm just going to sort of attach it over there. Let me just do this. And then you can see as I'm attaching. Okay, and you can actually see it's 4,431 megahertz, which is very, 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 very good and still stable. Although I'm touching it, the variation to wherever it's printed, and to the actual display on the result coming on the frequency counter from the instrument, measuring instrument, is about 10 hertz, which is extremely good. That won't make any difference wherever it is used, this particular crystal. Now, I think what we must do, let me just get one. Okay. All right, let's do it this way. What I'm doing is I'm just getting one adapter here. Just put it in a plastic bag. Let me just show you. Okay, now that's a test jig for a surface mount that I have made. And it's straightforward, okay? And it's very easy to attach, and that's what I'm going to do. I'm going to try to attach it now over here. Let me just see. It's but difficult with one hand holding, filming and talking and sort of trying to do things over here. All right. So right now we got a little jig inserted for surface mount. Okay. And the surface mount has got two little tags right at the bottom. Okay. You get them in metal can, you get them in ceramic bodies and various shapes and things like that. Okay, but this is just one of them. And I think this one here, as a matter of fact, I don't even know what the frequency is, but let's see. Let's see what our instrument tells us. Okay, it's 36861. 36861. Okay, and on the frequency, on the crystal itself, where it's written, is 36864. So it's less the difference, although there's a stray capacitance because of the jig and the wires, as I explained again earlier on. There is always discrepancy between what is printed and what is going to show over here. But over here we're talking like less than 10 hertz on on 4 megahertz tapotin. Or nearly 4 megahertz, correct, yeah. So it's actually extremely good, even with these test jig. The instrument and the crystal tester is giving us extremely good results. And of course, the accuracy also depends on your frequency counter. All right, so right now with a adapter, I don't have to even remove it. I can take, let me just take, say for example, I'll take this one and this one, let's see, what is it? It's about 15 something megahertz, 15.7 something. Let's see what it says, okay? Okay, let me just hold it. Oh, sorry, let me just, I'm not making a connection here. Let me just try to, come on now. All right, there we go. 15, oops, sorry. I'm not making a connection. Okay, it's 15.7603, which is very, very good. For me, holding the crystal and the stray capacitance and inductance and so on, I'm still getting extremely accurate results with my crystal tester. that we make and supply, let's put it that way. Okay, so I can right now speed up, and I can take from a batch of crystals, and within few minutes I can measure actually several hundred. And you can see I remove it. Okay, let me just do this, and the moment I touch, the moment I remove, the moment I touch, it gives me instantaneous reading, which is extremely good. All right, now maybe you've seen okay, let me start over here. In the data sheets, okay, manufacturers, they specify crystals that can be manufactured for many different sort of applications and timing oscillators. I'm not going to mention all the possibilities, but nonetheless, wherever the crystals are used, you basically get two different types of crystals. When I say two different types, two different aims where you're going to use the crystals. And according to this manufacturer, they specify one lot that they manufacture from 1.8 to 40 megahertz. They are fundamentally designed to operate when they're manufactured at a fundamental frequency, in other words, intended frequency. Then yet you do get a different type of sort of crystals, although they look identical, from 20 say to 105 megahertz, which is extremely high frequency and very difficult to manufacture, very expensive to manufacture. So with the clever sort of techniques, what they do is they exploit harmonics of any crystal, where it's a fundamental, made for fundamental sort of frequency, this sort of predominant, or on the specific sort of harmonics you want to use the crystals. What they do is, due to the clever manufacture, as I said, they use usually a third overtone or third harmonic predominantly. Of course, it can be used on many different harmonics, but they try to enhance the operation of the crystal at the third harmonic. So the crystal doesn't have to be, because say for example you need 100 megahertz. Now that crystal is going to be very, very, very small, very thin, very brittle, and because it vibrates at such a high frequency, it will break easily. So now it's easier to make sort of 3 times lower frequencies than 100 and make it operate as a fundamental sort of frequency, and then just operate it on a third harmonic. It's maybe a subject for some other time, but the reason why I'm mentioning this is because I'm going to show it to you right now. Okay. Now let's assume, okay, this specific crystal, it's a 28 megahertz. Let's just go. Okay, it's 28.825 megahertz. So if I put it, theoretically, if it was made for that fundamental frequency, if I put it over there, it should give me 28.825, but it's not. It's made, fundamental frequency of this crystal is much lower than that. Okay? In order to make it a bit more stable and easier to manufacture, and the crystal is more reliable. So it actually, that is a third sort of harmonic that it actually operates on, top of 10, although the fundamental frequency is 20, you will see it right now. Now let me just put it in the jig and then see what does it tell us. Okay, let's see. Can you see there? It shows us, although it's in its data sheet, it says there, it must be used on a third overtone to obtain 2825. Yet it shows us over here 9,543 whatever, 9,6, okay, because of my hand touching it or whatever. Earlier on when I measured it, I measured 9,61507 megahertz, which multiplied by 3, which is a third harmonic, and over here, third overtone or harmonic, some people they call it, which should be actually harmonic, but some people call it overtone. It gives us precisely 28,825 megahertz. So I'm just bringing it to your attention when you do get maybe my crystal tester, that you have to take into consideration and you don't get confused. Maybe you read specific frequency on the crystal, excuse me, like over here, maybe you can see, maybe, let me just put it over there. Let me, no, that doesn't matter. Okay, 28 something, I don't know if you can actually see it, 825, but yet we're measuring 9,615, okay, which is the original fundamental frequency. Okay, so just be aware of that. Now let's take even a ceramic sort of resonator, and this specific one, it's made for 50 megahertz operation. I've already done the summary over here, 50 megahertz. Yet when we put it in a jig, let's do it. Let me just remove the actual, let me put the phone down, camera should I say, okay, there we go, and then we take, and then we put into the socket the 3-pinner, 50 megahertz, and let's read what it says there. Aha, although this one is manufactured and sold as 50 megahertz, okay, it's not showing us 50 megahertz, showing us 15,1573 something, okay, which over here I have done in a previous 15,1619 megahertz. But remember again, that is fundamental frequency. Multiplied by 3, that gives us about 47 megahertz, okay, which is very close to 50 megahertz, because remember again what I said earlier on, that these type of sort of ceramic resonator crystals, they have got a much greater tolerances than the actual sort of metal, sort of crystals, because they are cheaper, much easier to manufacture, and so on. So again, be aware, if you don't get a reading, then divide it by 3 whatever, or multiply by 3, and then that would be the actual operating intended operating frequency of the actual crystal. And so this one here, although it says, as I said for the last time, okay, although it says 50 megahertz, let me just do it this way, okay, it measures 15,619. So just be careful, you got to understand that. Of course, you can do your own research, because I'm not really giving the lecture on the crystals. I'm just trying to demo my little crystal tester that I make, to supply my customers and whoever sort of has got the needs for it and things like that. Yeah, on that note, I hope I sort of explained it well and you enjoyed sort of this long video. But unfortunate, in order to be able to demonstrate it, I had to use quite a few crystals, for you to sort of get an idea, accurate. And I'm very, very pleased with the instrument, and I'm not aware of anything that's really so cheaply available and so highly accurate test jig instrument, or whatever you want to call it. and capabilities that it can measure surface mount and it can measure conventional or just about any crystal. Yeah, on that note, thank you for watching Batos crystal tester.